Hi there, these are the recordings for problems 27 and 28, and both of them use a concept called law of sines. Law of sines. So I first need to recap what is the law of sines. It is related to SOHCAHTOA, but you can use it even with non-right triangles. So law of sines says this: when you have a triangle, we're going to call this A, B, and C. And this is side A, side B, and side C. That it says this, that the length of side A over the sine of the angle A is proportional to the length of side B over sine of angle B, and is proportional to the length of C, which is, and proportional to angle sine of angle C. Keep the color code straight here. So the sine of this angle proportional to its side length is equivalent to the sine ratio of this angle proportional to its side length, and this angle proportional to this side length. So it's one giant proportion. Now, generally, when we work with this, we don't use all three, or not generally, we don't use all three. This original theory just says all three combos are possible, but when we actually work with it, we only deal with one proportion at a time. Something over something equals something over something. By the way, if you were to Google this, you can also see it in the inverted form. If you flip all of these or invert them, it does the same thing. So that is the law of sines. You use the law of sines, and this is generality. There's a couple exceptions, but I don't want to get into this at the moment. But you use the law of sines when you have a triangle problem, when you have more angles than sides. More angles than sides. Just to give you a heads up, there's something called law of cosines. Most likely you're going to see that pretty soon. And again, this is a generality. There's a couple exceptions. I'm not going to deal with the exceptions right now. The law of cosines you use when you have more sides than angles. So just keep in mind, law of sines, more angles than sides. Law of cosines, more sides than angles. So one step at a time here. So we have a ship sailing due north. At a certain point, the bearing of a lighthouse, which is 12.5 kilometers distance, is north 38.8 degrees. Later on, the captain notices that the bearing of the lighthouse has become south 44.2 degrees. Question: how far did the ship travel between the 2 points of observation? So we have a ship here. I attempted a sailing ship, and we are heading due north. So at a certain point, we have a lighthouse spotted at 38.8 degrees, and that's from the north line. So we go like this, and we have 38.8 degrees from the north line. And we have a lighthouse that lighthouse is 12.5 kilometers in distance. Take care of that. I tend to cross things out when I take care of it so you don't get lost. Later on, so we're still traveling north. Doesn't change bearings here. The bearing of the lighthouse has become south 44.2. And then it says here that the lighthouse at a second bearing point is south 44.2 degrees. So south from south, 44.2 degrees. We're going to close it up. So we have one side and two angles. More angles than sides, we use law of sines. The goal here is to find how far did the ship travel, so that is our x. So to work with this, we have to find the angle that's directly across from x, which we can do because we know triangles add up to 180. So we're going to add 44.2 plus 38 plus 38.8. 10, carry the 1. And that's going to be 5. So that's 13. Carry the 1. And that is 83. Taken away from 180. And of course, that's going to be 97 because we're going to borrow. It's a 317. So it's 97 degrees. So we find that this is 97 degrees. So law of sines works with the sine of the angle with its opposite side. So we're going to do the sine of 97 degrees over x. You could flip that too. It really doesn't matter. But you work with the angle and its opposite side. And then we have to find the angle that's opposite of this. So that's going to be the sine of 44.2 over 12.5. It's really important in general, you don't touch a calculator until your variable is completely by itself. So we're going to cross multiply, keep parentheses around these. Okay, x is not still by itself yet. One more step. So to solve for our unknown x, it's going to be the 12.5 times sine of 97 degrees over sine of 44.2. This is a lot easier to do on a TI-84 calculator, but I'll see if it works on the computer calculator. Okay, so let's see, that's going to be 97 sine. I'm going to go this way. 97 sine times 12.5 divided by 44.2 sine. That looks about right. There it is, 17.79. If we round, we'll go 17.8. And then it's really nice just to ask yourself if this just makes sense. K, M. And one of the things that you can say makes sense here is that if this is the longer side, this should be the larger angle. So 97 goes with the longer side, 17.8. A smaller angle, 44.2, goes across from the smaller side. So just kind of a check visually that that is true. Just so you can visualize this, think of it as, if you have an angle, think of the distance between your fingers. The bigger the angle, the longer the distance between your fingertips. And the smaller the angle, the shorter the distance between your fingertips. So as you solve, your answer should kind of follow that rule logically, which in this case it does.